In this example, I'm going to use linear interpolation to estimate the values of the enthalpy and the entropy of water vapor between measured points. Now, if you've taken a thermodynamics course before, then you will probably have used this many times if using a table such as the one provided here. And you'd have to see where does your temperature fall, what values does it fall between, and then by hand manually do the linear interpolation. We're going to have Matlab do all of that work for us. So the table shown is just an abbreviated table that only goes up to 100 degrees. We're going to use a bigger table that goes all the way up to 374 degrees, everything in Celsius. So if we look at the CSV file called L06 steam table, we have here, through experiment, a bunch of different temperature measurements, and then we have the ones we're interested in for this example is we're going to look at the enthalpy of the gas, and we want the entropy of the gas. That's going to be the water vapor. So our temperatures are all in Celsius, and then the enthalpy is in kilojoules per kilogram, and the entropy is kilojoules per kilogram Kelvin. And just a little bit of background for what are we actually looking at here. We're trying to see enthalpy is roughly the energy of the gas. So we're going to see as the temperature changes, the energy that the water vapor contains is going to change. And entropy roughly is a measure of disorder in the system. So that is also going to change as temperature varies. But really what we care about for this example is just looking at the data and how we're finding these interpolations. We're not going to be worrying too much about interpreting our data. One thing to note also in this CSV file, the first row is all of my header information. These are strings, they're not numbers, so I want to be careful when I do import this CSV file. Alright, so I'm just going to import this using CSV read, and it's L06 steam table. Now, like I just said, we want to be careful because the first row is not going to be numerical data, so it should not actually work for us. I need .csv here. Alright, so it doesn't like that because, again, that first row has non-numerical data in it. So what I can do is similar to when we used XLS read, I can specify where to start. Now it's a little bit different. I don't specify a range, but I specify how many rows down to start and how many columns over to start. So if you see here the way they want it, I want to start not on the first row, I want to start one row down. Right, so when I can add extra arguments here, I want to start one row down, but 0 just means start at the first column. So it's how many rows from the top you want to start. The default is 0. I want to start one row down. How many columns from the left do you want to begin? I want to start at the extreme left, so I don't want any columns being skipped over. So one row down, but starting on the first column. So now we see that I can import that because it's only importing this numerical data. And I'm going to suppress that now. So that just imported this entire data range, but all I care about for this example is I have my temperature as my independent variable. I'm going to have two dependent variables I'm looking at, the enthalpy of the gas and the entropy of the gas as well. So I'm going to call my temperature measurements T, and that's just going to be the first column of data. Again, temperature is in column number 1. Right, so those are all my temperature measurements. Those are all my independent variables. I then want my enthalpy, which I'll call little h. And for this example, I'm looking at the enthalpy of saturated vapor, or in the CSV file, it's called gas. So going back here, that is column I, which means I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9. The 9th column is the gas entropy. So this is going to be the 9th column of A. And the entropy, if this is 9, 10, I want the 11th column to get the entropy of the gas. So that's going to be 11. So I'm only going to begin by looking at the enthalpy. Once I have that, then I'll start looking at the entropy. So the first thing I want to do, similar to when we did curve fitting, I just want to plot my raw data here. I'll just use the plot command for this. So independent variable t, and I'll start just with enthalpy. And I'll put this as black circles for my actual raw data here. Make this a little bit nicer. This is going to be the temperature in degrees C. And this is my enthalpy in kilojoules per kilogram. Alright, so from my experiment or from my collected data, these are the actual data points that I have. Those specific temperatures which, through my experiment, I was measuring what the enthalpy of the vapor was. Alright, so all these discrete points are what I have here. And fix my spelling there, temperature. And if I zoom in, or if I go to my actual Excel sheet, my temperature, I have a measurement here at 23. From this data sheet, I have a measurement at 24, but I don't have a measurement at 23.3. So what I can do is use a, just for now, linear interpolation to estimate what that value should be. So remember, the linear interpolation is really just a weighted average between the two values. So between 23 and 24, if I look at enthalpy, which was I, it should be between 2543.5 and 2545.4 is what we expect it to do. So I can use that interp function. So I can take my independent variable t, my dependent variable h, and then for this part of it, I just want to make the linear interpolation estimate as to what the enthalpy is at 23.3. Right, so I'm getting 2544 as my estimate. Again, looking back at the data, we expect it to be between 2543.5 and 2545.4, and we see that it does adhere to that. It is between those two values. And it's doing that same calculation that we saw in the previous slide of that weighted average between those two neighboring points. Now, one thing to keep in mind here when we're using interpolation, at least in one dimension, is that the independent variable, or really this first argument here, has to be strictly increasing or strictly decreasing, meaning that in order every value has to be higher than the one before it or lower than the one before it, otherwise it's not able to do an interpolation. So for example, if I look back at my raw data here, if I were to use h values, which are not strictly increasing, they increase but then they start to decrease, I'm not going to be able to do that because of that. So if I actually wanted to estimate temperature from enthalpy, which I can do this in reverse sometimes, but here I cannot, because let's say I wanted to know what's the temperature when the enthalpy is 2600. It's not going to do that because the value of h is not only increasing or only decreasing. However, the value for temperature I put in is only increasing in this example. Alright, so the first part, just the estimate of the enthalpy at 23.3 degrees Celsius. Now I want to look at what does the interpolation look like across that entire range. So I want to estimate the temperature everywhere based on these however many 120 data points I have. I want to estimate everything in between the range that I measured. So I'm going to make a linspace between the minimum temperature I have and the maximum temperature I have. And I'll use 1,000 points for this example. And what that's going to let me do is now make what I'll call enthalpy estimates, because I can use interp1 not only with just a scalar like I used here with 23.3, but I can put in my dependent variable, or my independent variable, my dependent variable, and then here TE is as we see, a vector of values. If I run this, if I put in a vector of values, I get out a vector of values. So for each value of TE, this is giving me the corresponding estimate using a linear interpolation of the value of the enthalpy. And one thing that I should specify here, if I can put a fourth argument here in, linear. By default, if there's nothing there, it uses a linear interpolation. But here I want to explicitly put linear here, because when we go to cubic, we're going to see that it's different. This way we remember it's doing a linear interpolation. And if I hold on to my previous figure, I can overlay now on top of the raw data the data I get from the interpolation. Make that a little bit bigger. Right, so again, the black circles are the actual data I have, and the red line is now using a linear interpolation, filling in the spaces in between. So you see, for every point we have, it's just connecting all those points with a straight line between them to make that estimation. And we're going to see that's going to be different than when we go to a cubic spline in the next section, how it connects those points. Now the idea of using the linear interpolation is that every line, so there's a line from here to here, and another different line with a different slope from here to here. The edges of all the lines share the same endpoints, but not necessarily the same slope. That's different in the higher order interpolations that we're going to get to. All right, so we filled in kind of those missing pieces in between data points. We were able to make a interpolation at 23.3 degrees as to what our enthalpy was. Now we're interested not just in the enthalpy, but the entropy too. I haven't used this S yet. So I really don't have to change too much at the moment. Let's go back to line 20 here. All right, so that was my enthalpy estimate. I can actually use in my dependent variables, I can put in multiple dependent variables here. So I can actually put in H and S and rerun line 20. We see here that now I get two results out. The first column are the enthalpy estimates, since H was first here, and the second column are my entropy estimates, since S was second. So based on line 20, I'm evaluating both, I'm doing an interpolation on both H and S. They share the same independent variable, but I'm doing both of those at 23.3, so I get the same result for H, and now I get this additional value. That's the estimate of my entropy at 23.3 degrees. Similarly, if I go down here to line 24, where previously I'll unsuppress it for the moment, these were my enthalpy estimates at 1,000 different points between my minimum temperature and my maximum temperature. I can again put in here multiple dependent variables, and now if I run this, I see, looking at HE, running this, looking at HE, it now has two columns of data, where again the first column are actually my enthalpy estimates, and the second column are my entropy estimates. So I actually want to change this because I want to distinguish them in the next step. So I'm just going to call this B for the moment. That way I can say that HE is just going to be the first column of B. And I get back those enthalpy measurements like I had before. I get those same results on my plot. Oh, let me get rid of this for a second. Right, replot this. All right, so everything looks exactly the same. But now I can also get my entropy estimates using the second column of B. All right, so those are all my entropy estimates. Let me make a second figure now, looking at my entropy. I want to plot versus S, not versus 2. There's the entropy. Right, so this is again from my raw data, the entropy measurements at all of these various temperatures. And now, just like I did for enthalpy, I want to plot on top of this the estimate I got out from that linear interpolation. Right, so again, based on that red line is filling in those gaps, all the entropy measurements in between those that I actually measured. Right, so summing it up, I have this figure 2 is entropy using the raw data and a linear interpolation between the points. I have my figure 1 for the enthalpy doing the same thing. I used here just a linear interpolation on 1D data using interp1. And we see we have to have this independent variable either strictly increasing or strictly decreasing. And then we can put in our dependent variables, either one or we can have several, and then the points at which we want to run this linear interpolation. So in the easy example, I just want to know both of those values at 23.3 degrees, and then later I can put in a whole vector of values there and then visually see what that interpolation looked like.